Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by SatSearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. I'm joined today by Tony Schoenherr and Alexander Reissner from SatSearch member company Impulsion. Impulsion is a space technology company based in Austria. It was founded in 2016 and today focuses on advanced propulsion technologies for small satellites. Today we're going to talk a little bit about field-emission electric propulsion, or FEEP. This is a form of propulsion that uses liquid metal as a propellant and that enables a satellite to change orbits, reposition for different applications, maneuver out of certain paths, and so on. Before we start, hello and welcome Tony and Alexander. Thanks for being here today. Could you each just say a little bit about what you do at Impulsion and maybe if there's anything you want to add to that introduction I just gave?
Yeah, happy to. Good morning. Thanks for having us. It's really great to be here on this podcast. My name is Alex. I founded the company Impulsion 5 years ago. We just celebrated our 5th birthday, and I did not imagine 5 years ago, where we would be right now, supplying multiple constellations and customers all over the world with propulsion solutions. So I'm really happy to talk to you about what's going on in the market right now.
Excellent. Thank you.
So hello from me. I'm Tony. I'm the product manager for the Nano family of our thrusters. That includes the heritage product of the Impulsion Nano, which is now with more than 60 units in space, and as well as the new products that are coming soon to the market that include a product called the AR3, which will be suitable for thrust vectoring. And I joined the company 3 years ago. It's been a bumpy ride, but a good ride. And it's great to see that the technology is coming alive as we go along.
Well, fantastic, guys. Congratulations on the progress and happy birthday to Impulsion as well. Right, so let's get into the technical details then of the of class of technology that we're talking about today. So first up, I was wondering if you could please tell us a little bit about the history of FEEP technology, sort of touching on the maturity in different applications and how this has driven the development at Impulsion.
Yeah, I guess I'll take this one, having been following this or part of this development for almost 2 decades. So when I joined this technology development program in 2008, it was already an old technology in the sense that it was driven by a technological pull from the European Space Agency. Right there, we were flying liquid metal ion sources for huge scientific missions, but never for commercial applications. Right? So I'm coming from this kind of academic background, right, developing these scientific instruments with liquid metal ion sources. And then over the years, we developed that into a propulsion technology used to really find precision scientific satellites, still together with the European Space Agency. And then in 2016, as you mentioned at the beginning, right, we figured, with all the constellations coming up, there was a need to position small satellites, and we had in the lab already a propulsion system that was meant to produce a precise small thrust, right, that was suitable for this application. And yeah, that's when I changed, kind of switched gears from an academic career into an entrepreneurial career, and I founded Impulsion. Gathered a great team like Tony, and 45 other great engineers, and kept on developing this into an industrial product, right? With the first units coming directly out of the ESA development stage, and then further developments having more of an industrial approach, of course.
Right, fantastic. How challenging did you find it to take the technology from the sort of ESA research area into the industry?
Well, I have to be honest with you. I completely underestimated that in the beginning, right? I thought we have a working prototype, why not just, sell it, right? But that's not how it works, right? So the phase of an actual industrial product development and then the huge effort of industrializing something, right? So putting up the production. I mean, we spent millions and years coming up and setting up a production that is today ISO 9001 certified and audited by major space platform providers. But setting that up spinning in automotive technologies, in production, airplane, production measurements and so on into the space industry was really, as Tony mentioned, it was a bumpy ride, but it's just super interesting, right? And it was not something I would have anticipated to be the major kind of factor in the beginning when I founded the company. But now that it's kind of done, it's kind of logical, right? So, yeah.
Oh, interesting. I think that's maybe a topic we could talk about another time with all those different aspects. So, to bring it back to the technology, the FEEP thrusters, an important aspect of this technology, I know, is thrust vectoring. It's the ability to control the direction of thrust in different situations. It's one of the main requirements in attitude and orbit control systems in space missions. For that specific setting, are there any advantages to using FEEP technology?
Yes, so indeed, the thrust vectoring capability is something that we're now introducing within our new product line. And it's been something that has been around for as long as people are flying spacecraft with propulsion, because essentially every propulsion system has an intrinsic offset of the thrust vector. So there are necessities to compensate for that. And there are different ways to do that. So if you're staying close to Earth, you can use the Earth's magnetic field in order to orient your spacecraft a little bit. If you go further away, you can use cold gas systems to steer back to the thrust direction that you wanted to. Or if you're on a larger spacecraft, you can put the propulsion system on a gimbal mechanism in order to basically turn the entire thruster into the direction that you want to shoot at. But all of these solutions are heavy and cost intensive. And especially when it comes to mechanisms, I was always told by my former colleagues at ESA, the best mechanism is not to use any mechanism at all, because it's very prone to failures and there are a lot of difficulties in making it happening in a way that at some point the mechanism becomes more complex and more expensive than the actual propulsion system that you're trying to direct. So in FEEP, we have the advantage of being able to control the thrust vector just by shaping the electric field that is used for the acceleration of the extracted ion beam, which means that if you just adjust the electric field by putting a different electric potential in the area where the extraction of the ions is happening, we can redirect the beam without the need for any mechanical parts, without the need for anything heavy or complex. It just adds a little bit of a complexity to the PPU in the high voltage setup of the thruster. But you're basically able to add this thrust vectoring capability without adding a lot of system overhead onto your spacecraft. And the advantage here further is that you can put it on the spacecraft without designing or redesigning the spacecraft in order to compensate for the propulsion system, which makes it also very easy on the integrator side than to say, okay, well, I put the propulsion system there and you don't have to worry about it. It's rigidly there. And if the performance of the thruster then is suitable for the mission, it's really nice for the satellite integrator then to say, okay, this is it. This is all I need to do. And of course, this is very interesting for the market and also for scientific missions, especially ESA and all the other agencies, because it saves a lot of mass on small satellites, right? So if you don't have to have a cold gas system, if you don't have to have a gimbal, or at least not so much propellant for the cold gas system, then you can save mass, and that might even be enabling certain missions that were unthinkable prior to having that capacity. So if you think about small satellites, especially CubeSats that don't really have a lot of mass, don't have a lot of volume, being able to redirect the thrust vector within certain performance limits is certainly a mission enabling technology. So that's really what we're striving for here. Also, if you save mass on the spacecraft, you can also use that for additional payloads. So even if your spacecraft is not changing in overall, but you have more space and mass for the things that you want to do with the spacecraft eventually.
Excellent. Yeah, that makes a lot of sense. So obviously, as some of the potential applications and constellation management, etc., expands and the more advanced capabilities are brought in, there's the opportunity for satellites to use multiple thrusters on a single satellite. How do you test for issues where there may be thrust vector misalignment and ensure that applications such as orbital transfer, there's no problems with such misalignment?
Yeah. What we do when we produce our thrusters is that we characterize all the thrusters to the level of detail that is required for this. So we go through a nominal acceptance test campaign where we test for the typical environmental loads. So we have thermal cycling, we have a vibration test to check for failures in workmanship, so to say. But we also have a performance characterization right before we ship any thruster, where we also characterize the thrust vector offset to a point where we can communicate that to customers if there's any issue with that. So a customer knows exactly where the thrust vector would be after he receives the thrusters, and then can plan accordingly in order to switch thrusters around, or even if they have several missions, they can also switch thrusters between missions in order to compensate for anything there. Of course, we are trying to always keep the thrust vector offset as minimal as possible, but reality sometimes tells us a different story there. And then if you have the capacity of being able to control the thrust vector, of course, then it gives even less worry for the integrator, because then over life or the COG of the satellite changes, for example, they can readjust for their thrust vector there, and then that really aids in making the mission successful over time.
Right, fantastic. With the thrusters that Impulsion provides, or FEEP thrusters in general, FEEP technology in general, is it possible to use the systems in pulsed mode for precision station keeping or similar uses?
Yeah, so the advantage of FEEP technology is that the time that it takes in order to get to a thrust is very, very short. And it's also very stable. So it takes a few seconds if you command a thrust in order to get to the point where it stays stably at that thrust level. And if you shut it off directly afterwards, it's no issue for the thruster. So if you only need a small thrust level for a few seconds, this is certainly something within the capacity of the FEEP technology. And at the same time, you could also fire it for hours or hundreds of hours continuously if you decided to do so. And that makes it very versatile in how you can operate it. It's not directly a pulsed mode, so there's no pulse you can command, but you can switch it on and off in a very rapid manner in order to create very short impulses that could be used for precision station keeping. And here we also have the advantage that we can really predict very well the thrust level with the electric parameters that we can set. So of course you can go to the full maximum thrust, but you can also go to a very low thrust level, which would then enable this precision station keeping even further, because you're reducing basically the level of push you give to the satellite in a certain direction.
Okay, fantastic. So far, we talked about various situations which are perhaps a bit closer to Earth and in the different orbits of Earth. Is there a potential to use FEEP capabilities for deep space missions?
Yeah, so a lot of customers obviously stay close to Earth because there's also where there's more market for their businesses, basically. So in Earth observation, communication, that's mostly happening around Earth, obviously. But if we look into scientific missions that want to go further into deep space, then it becomes really interesting, because you want to use a technology that can enable this mission. And especially if you go into very deep space, the delta V that is required in order to get there reaches values that makes it very challenging for chemical or other electric propulsion systems. So you need a very high specific impulse in order to enable that. And also, as I said earlier, if you leave the Earth's vicinity, you're losing the capability to use the magnetic field in order to change your attitude of the satellite of spacecraft. So you would have to go for heavy cold gas systems in order to redirect your satellite into the right direction, which again, is heavy. So if you're able to use a system that combines a high specific impulse with the additional capacity to redirect your thrust vector without the need of a heavy mechanism or cold gas system, then you're really in a good shape on the overall system, and you can potentially enable missions that were not thinkable before. Even if you go to deep space, as long as you are able to provide the power. So that's the downside maybe that comes with all electric propulsion at a point where you have to say, okay, the further you go away from the sun, the less power you have available on your solar panels. But given that our small technology thrusters start at very low power levels, this is something that is even possible even if you go a bit further away from the sun.
Interesting. It's good to have that flexibility as the industry progresses and as we see different missions at different scales, or sort of the activities of the big agencies lead in potential downstream applications for the smaller companies. So to bring it back to Impulsion specifically, could you tell us a little bit more about your Nano AR3 product? How was the product conceived, and what are the advantages or characteristics about it compared to other competing products in the industry?
As Alex was mentioning earlier, the company was founded on having FEEP technology to a point developed where it was suitable to put into a thruster and to a propulsion system that could fly. And the Heritage Nano, as it is called now, was a good way to integrate the technology to a product that can serve the market, that can serve the needs of our customers. But as it is with every customer, they always want more, right? So the questions here and there, like, oh, could you also add that feature, or would that be possible with the technology? And of course, you listen to your customers and also to feedback you get from other players in the market and from the agencies. So we take these ideas and then we look at, okay, what is really what the market needs and wants, and we see whether it's feasible with the technology we have available. So the idea of using FEEP for thrust vectoring has been around already for a couple of years in the company and in our research partner. And we've did a few studies just to see whether the feasibility is even there, like whether our idea of redirecting the beam is actually feasible. And we figured out, yes, it is. And we took that idea and grew it into something more and more suitable for space application, to a point where we developed the PPU further. We had to develop the software further in order to actually be able to control the thrust vector in a way. And then, of course, the thruster itself had to grow and evolve into something that can host this capability. And then the Nano AR3 came to life as such as a result of that. So it's been a path of a couple of years that was really driven by the market need for this capability. And eventually we have first customers that are really interested in getting their hands on it, want to fly it as soon as possible, because they also see it as something where they could make benefit for their mission with it.
That's interesting. So what sort of missions and what sort of environments is this thruster suitable for?
Yeah, so as Tony mentioned, this thruster AR3 has a rather long history in its development, but it's not a standalone development. It's part of a new family of thrusters, and we call it the R3 thruster family. And the R in this acronym really stands for resilience and reliability. So what we did over the last years is kind of following up on the quality improvement in our manufacturing and all this setup of industrialization. Also make a huge step in our product development in going from a COTS-based product, like early stage, new space, kind of suitable product, to a really industrial space product, right? That includes, higher radiation tolerance. It includes single event tolerant designs, all the things that you would wish for if you had a kind of heritage space, high reliability supplier, but you don't want to pay for it, right? And the reason why we were able to kind of introduce this new family of thrusters that is still a very reasonable prices is that we can build on volume, actually, right? So we have all those customers and all those constellations that we supply using the nano thruster, the classic nano thruster, waiting for an upgraded, higher reliability product. So we had a reasonable certainty about our market and how many products we can produce and we can sell. And as you mentioned before, the key really for combining high reliability with low prices is standardization, right? So having a standard product that is versatile, that can fit multiple needs, is the only way to ever get there, because there will never be a one-size-fits-all solution for propulsion. Everyone has different propulsion needs. So this standardization, modularization is really the key. Coming back to the AR3 that we've been discussing before, it uses a lot of building blocks from the R3 thrusters and another one which is called IR3. So there's three thrusters, kind of share a lot of common building blocks, share the same production line, product assurance, and so on. And in that sense, it is suitable for a very large envelope of environments. We have customers, as Tony discussed, using the AR3 in non-LEO missions, going far away and actually using the vector to desaturate their reaction wheels, so to reorient the spacecraft. Right? We have customers building very agile platforms, right, in LEO to have a lot of maneuvering capability there. So I think the step to go to a class of thruster, a new kind of define a new standard for propulsion systems for small sats with this R3 class is really was the right approach to get this kind of flexibility into the market.
Right, excellent. Now, you mentioned that you use lots of market insights and space agency feedback in the development of the Nano AR3, and also, as you've just explained, that this was something of an evolution in the product line. But how did you find? I guess a big question: how did you find the industry's initial reaction when you launched the product?
Well, obviously, we're kind of biased here because we are selling the product. I have to be honest about that. But the reaction was really impressive, actually. I mean, I had the impression that people were like, wow, this is actually possible, right? So the kind of astonishment of having, because we told them, look, it's the same thruster, right? So it's not even bigger, yeah, and it just can do that as well, right? So if you compare the R3 and the AR3, and that was really puzzling for people. Obviously, it's still not for everyone, right? So there's a lot of applications that don't need that, and the majority of our customers, will use the standard R3 thruster because that's they have other systems, they have the magnetic field to rely on, they have to they have ways to orient the spacecraft and desaturate their wheels. So it's again not a product for everyone, but the fact that it is, and that's what I like so much about this specific product, the fact that it's bringing an additional capability to the market is enabling new business cases, but also new exploration opportunities, right? And that's so rewarding for us, right? To see that, bringing this capability to the market then drives eventually innovation, on platform level, on mission design level, and so on. So I don't expect everyone to use it, right? And that was certainly not their reaction. But the cases where it is used are the cases that really push, boundaries of what's possible to do with small satellites that cannot have a mechanical gimbal and so on, and were limited by that before.
Right, fantastic. Well, it's clear that a lot has been put into the development of the product, and for Impulsion, things have come a long way. So I guess just to finish up, you mentioned there that the product is enabling new exploration opportunities and new business cases. I wondered what you were most excited about, looking forward to in the future of thrust vectoring in propulsion.
Yeah, I think mobility in space is in general something that is very near and dear to my heart. I think it's a key topic that needs to be addressed in the proper way in order to avoid kind of environmental catastrophe in space, right? So we have this gold rush situation, and everyone wants to support that. And I'm certainly happy, about all the growth we see in the space industry, and I really think that space as a resource is extremely valuable for a lot of people here down on Earth. But in order to use this resource in a sustainable way, the key is really to have reliable and flexible mobility in space, right? We need to be able to reposition assets in space. We need to be able to safely deorbit things. We need to be able to kind of clear up space if we need to, and so on. And being at the forefront of providing this mobility, is really, I think, a huge driver for the whole team over here. And in that sense, I think features like thrust vectoring, higher thrust capabilities, higher reliabilities for specific missions and so on. Those are then the results of a very intense dialogue with the industry, understanding where they want to put their assets, how they want to move their satellites around, what are the pain points, and what is the kind of mobility needs and mobility solutions that are necessary in order to make it easy and cheap, honestly, for everyone to be responsible, right, in terms of their own infrastructure in space. We don't have the regulations yet to be really, very thorough with a lot of things. That's why I'm comparing it to this kind of gold rush, Wild West situation. But then people are mindful, and if it's easy enough, to be responsible, then I think, that is a big push into leaving a sustainable situation for further generations.
Well, fantastic. I think that's a wonderful vision, and I love that idea. Make it easy for everyone to be responsible. I think that's a great way of looking at it. Thank you very much to both you guys, Tony and Alex. It's really interested to hear about the history and the future plans of Impulsion in this area. For everybody listening, if you want to find out more about the business, impulsion.com is the place to go. You can also find information on the products and services on the SatSearch platform. So yeah, I just wanted to say thank you guys, and I hope you have a great week.
Thanks so much for having us.
Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.